Okay, in the news, kind of the same thing I was telling you before, except this is a local one. Two interesting quotes. This is an article that came out yesterday in the Murky News. First one is this great quote about, the cloud isn't this big fluffy area up in the sky. That sounds funny, but I actually got called by a reporter recently asking me basically to tell him where the cloud was located. I mean, so people are really confused about this. And then the second one is just this interesting one. Basically, if you're in the Silicon Valley, there's data centers everywhere. As we talked about last time, you don't see them because people don't like to advertise it because only bad things could happen if people knew about them being there. So, all right, so that's in the news. I think the mic's on. Can you hear me, guys, back there? Yeah, should be okay. I'll raise a little. All right, so last time we talked about warehouse scale computers. That wasn't on the midterm, but it was the setup for what we're doing since then. And one thing actually that comes to mind, just remember we do have this policy with the midterm that you can, what's the verb? Clobber. You can clobber your midterm if you do better on the midterm stuff in the final. So unlike the Cal football team, you get a second chance. So, all right. So we're going to continue our discussion about parallelism. We're going to focus initially on this idea of data parallelism. So, here's where we were. Parallelism is one of our big 6 ideas. Last time we talked about this idea of warehouse scale computers and, what's happening with smartphones being connected to these, huge computers that are, on the other side of the internet, and some of the issues they're dealing with, failures, dealing with varying load over time, having to worry about energy efficiency. Okay, so that's where we got to last time. All right, this was a slide, I think, from the first lecture, and I just wanted to show it to you again because we're kind of hopping around in this a little bit, but this is the schematic of the class, right? We're going to look at everything from, what we're talking about today, which is these warehouse scale computers, all the way down to, logic gates and even the transistors that make up the logic gates. Okay, so throughout all these different levels of the system, you've got all sorts of parallelism, and we're going to talk today really about 2 types of parallelism. Okay, so request parallelism and data parallelism. All right, so let's talk first about request parallelism. I'm not going to say too much about it, but request parallelism is exactly what it sounds like. If you're running one of these big infrastructures, in order to pay for it, in order to keep it busy, you want to have lots of stuff going on at the same time. You can handle different requests as long as they're not dependent on each other in parallel. You can handle them simultaneously. So, if you have a bunch of independent requests, like, a web search or like, a request for a Facebook page or something like that, why not serve a bunch of those up at the same time? You've got all these resources to use. So the key point here, and this isn't true of all the parallelism we're going to look at, but in this case, in this case, wrong button, the computation is easily partitioned, okay, across, it says within a request, we'll talk about that when we get to MapReduce, but also across different requests. Okay, so if I do a web search and you do a web search, there's no reason for those things to be dependent on each other. Okay, so we're going to take advantage of that. So let's talk about web search first. This is it says Google, but this is true of any web search. Well, we'll look at this, but the key components are, some request comes in. There are services over here where you're doing things like spell checking, getting ads. We'll talk a little bit about that in a second. The real processing happens down here. Indexes are basically lookup tables or trees that help you do lookups. And then probing for the index for the terms that you're looking for the keywords you typed in the search box. That tells you which documents are relevant. You pull those out, do a little more looking in those documents, and then you can spit out the answer. Okay? And what this is trying to show is, once these requests come in, the index server is spread across lots and lots of machines because it's big, and the document also spread across lots of machines. So that's where the opportunities for parallelism start showing up. All right, So let's say you wanted to search for a random term, say Dan Garcia. All right, so let's do that. I did that this mordan. And what did I get? It's a little, maybe it's a little too much, too much information here, but that's what I got. And you'll see, you'll see a couple things about Dan that we might not have known. One is, I don't want to go there. The other is his discography. So all of his CDs that you guys, some of you guys have bought. If you haven't, you might want to consider that. His early life in Rio, I'd like to hear more about that. And you know, his earlier career as a basketball player and a convict. And oh, there he is playing his guitar or mandolin or ukulele or whatever that is. Okay, so what was the magic that made this happen? If you could use the word magic for that. Oh, I'm sorry. Something else? Oh, and yes. I mean, it's interesting, right? This is kind of, if you really are into full frontal nerdity, then this line here is interesting to you, right? That there are 20, you know, roughly 20 million things in their database that seem to have something to do with Dan Garcia, and it took them 0.22 seconds to figure that out. Yeah. So the question was, the number of search results is totally bogus, and I'd say that that's true except for the totally part. So it's not, you know, it says about, and the way they do it is they kind of look at the index and they get some idea of the size, but it's not completely accurate, absolutely. Uh-huh. Yeah. I see, that's interesting. So if they're processing it as you go along. Yeah, interesting. Okay. The other thing that you might find interesting is, you know, although Dan is famous and all, you know, when I did my search, I was at work and knew I was in Berkeley, California, and that may have impacted, you know, who showed up, you know, whether, you know, this guy showed up first or this guy showed up first, right? So there's a whole bunch of stuff going on. You could do a whole class on how to do searching. Like, in fact, you could build a whole multi-billion-dollar company on how to do searching like this. So we're not going to really get into today, but I want to talk a little bit about what happens in the context of 61C. So, you know, you type in your request. Where does it go? Well, you know, we don't know exactly, but we're pretty sure Google has, you know, order a dozen big data centers spread across the world. It probably goes to the closest one. Doesn't necessarily have to, but it probably does. Once it gets into that building, there's a box that sits in front that figures out, you know, where in the building your request should go. So it's going to go, remember we talked last time about servers organized into racks and racks organized into arrays or clusters. So there'll be some cluster or array that your request gets sent to. Within that array, there's going to be a bunch of server processes that can handle the request and put it together, put the answer together. And then, you know, there's a whole bunch of chit-chat that goes on. The web server has to go do a lookup in the index. So it asks the index, hey, do you know anything about Dan? Do you know anything about Garcia? Google by default does an and, right? So it takes the documents that have something to do with Dan, documents that have something to do with Garcia. It applies some magic priority, but it typically only gives you documents that have both Dan and Garcia. So it's usually doing an or. But there's ways to, if you look at the thing that nobody ever clicks on, which is advanced search, there's ways to actually get it to do other things. It returns, you know, a list of documents, and then it ranks them from the one that it thinks is the most relevant, you know, down. Oh, okay, sorry. The people online are not seeing the screen. So let's see what happens here. All right, so sorry to our friends in England and, oh, don't read my, don't make me do. All right. Okay, so, all right, so that's the beginning of that. All right, now at the same time as we're poking around, you know, in the index looking for the right documents, we also have to get paid, right? So we go over to this completely different system called the ad serving system, and it actually runs an auction to figure out which ads it should show on your page. I actually don't think it shows any ads on Dan's page. I forgot, we should have looked. And then it goes to a different system, gets the, while it's looking for documents, it also digs out images of all the various Dan Garcias there are in the world. And that's all happening in parallel. And then once you, get IDs of documents from the index server, then you can actually go to the document server and get those. And then eventually you have to put that whole page together and render it and send it back to the user. Okay? And, this 0.22 seconds, how much of that is happening in 0.22 seconds, hard to say, but, when you type in a search, at any major search search engine, you tend to get answers back, less than a second or less than a couple seconds for sure. Okay, and there's a lot of engineering that goes on to make that happen, and there's a lot of parallelism going on to make that happen. And if they were running, every request one at a time, it would never happen. Okay, because you'd get queued up behind everybody else. So it's all about parallelism. All right, so what do you have to think about when you're designing a big parallel system like this? Well, a lot of stuff. But there's some simple things you could do. One is you want to try to distribute, the different entries so that all the requests don't go to one place. Okay. You want to make multiple copies of data, and you want to do load balancing across these copies. So, if you have multiple copies of the index, you don't want to send all the requests to one copy. You want to spread them out, right? So that you get a nice even load and the systems aren't as busy. So, this redundancy is a really important idea. And if you remember, that's one of the 6 big ideas in the course. We'll talk about it more later in the semester. But this idea of making copies of things helps in a lot of ways. One thing, of course, is it makes the system more tolerant of failures. So if you've got 3 copies and one of those copies goes away, you can still find the answer in 2 others, right? So redundancy for fault tolerance is a big deal, and it's one of our big ideas. But also, it gives you opportunities like, all the requests that come in for Justin Bieber, which up until at least recently was about 50% of all requests going to Google. They don't all go to one server. They get spread out because you make multiple copies of that. And you get the more copies you have, the more opportunities you have to do things in parallel, right? Because that's what we're talking about is parallelism. Okay, so that's really all we're going to talk about in this class, I'm afraid. Maybe it'll show up again later. But this idea of request-level parallelism, which is just blind, a request comes in, I send it over here. A completely different independent request comes in, I send it over there. It's kind of the easiest kind of parallelism you're going to get. Because there's no smarts that you have to do. You don't have to worry about possible interference or how those things are related to each other. Okay? But it's a big deal. It's probably the biggest source of parallelism in a system like this. Okay? It just happens to be pretty easy to do. All right, so now let's switch to the second part, which is data level parallelism. And we're going to talk about that today and then all of next lecture as well. And there's really 2 kinds. There's the kind of data level parallelism that you do while the data's that you can do with data that's in memory. So you have basically one sort of overall thing you're trying to do, one program you're trying to run, one instruction you're trying to execute, maybe repeatedly, and you want to figure out how to get parallelism there. Okay? Well, if you have to apply those instructions or that instructions to different data, right? Rather than doing it one at a time, rather than going, apply the instruction to this piece of data, then to this piece of data, then to this piece of data. If I build my system the right way, maybe I can do multiple of those at the same time. So I could take a bunch of different, like if I had an array, I could take those elements 4 at a time and process, all 4 of those elements at the same time if I built my processor the right way. So that's the first kind of data parallelism, which is I've got data that's in memory. I'm in the context of a single processor or maybe multiple cores on the same chip. But it's not this big scale, cross-server thing that we just talked about. But then the other type is exactly that, where I've got tons of data, like in my search engine, I've got this big index. I've got an index of every word that shows up on the web and a list of all the web pages that it shows up in. You can imagine, right, with over a trillion pages indexed, that's a pretty big index, right? It's all the words in a trillion pages. So you've got data spread across many servers, across many disks. How do you do those requests in parallel? And that's really what we're going to talk about today, okay? So we're going to talk about the in-memory stuff a little bit next time, and then there's a project, I think it's project 3 that you get to live it. And then today we're going to talk about this coarser grain, this stuff that's across multiple servers, and that's also what the second project is about. We're going to do MapReduce on the Amazon cloud, okay? All right, so any questions about any of that before I dig into this one specific way of doing data parallelism? Okay, all right. So, we're going to talk, what we're going to do is we're going to use MapReduce. You guys have already seen MapReduce, I believe in 61A and in your homework or lab, the lab, or you're about to see it in the lab. And what it is it's a fairly simple but popular model for doing data parallel programming. Okay, and really what it's aimed at is scalability, which means I want to be able to solve bigger and bigger problems with the same amount of time, or maybe even faster. That's scalability. And fault tolerance, right? Because if you remember, in these big data centers, stuff is always broken, right? There's always servers that are down. There's always disks that have failed. There's always, network switches that stop working. So that the programming model wants to hide that complexity from the programmer. Otherwise, you would have to write every program, if the disk is still working, then do this, else go to the next disk, else go to the next disk. You don't want to write that program. You want to just say, get me this item, and you want the system to figure out how to do it, even if you've got some broken pieces in the system. All right, so that's what MapReduce does. It makes things scalable. You can solve bigger and bigger problems faster and faster, and fault tolerant. You can deal with a world where things are broken. Okay, this MapReduce model, I should have changed this slide more than I did. It says pioneered by Google. That's what most people believe today. And Google uses it quite heavily. Last numbers I saw was they churn through more than 25 petabytes of data a day. And remember, what's a petabyte? A million gigabytes? Or am I off by 3 orders of magnitude? Petabyte's a lot of data. I think it's a million gigabytes. So, so they go through lots and lots of data. The reason I said it wasn't maybe not exactly pioneered by Google is, as I probably told you guys, my main area of research is databases. The first project I ever worked on was something called a massively parallel database system. And if you looked inside what was going on in that database system, it's exactly this kind of map and reduce thing. There are certain things that you do on single processors, and then you want to combine the results. So, buried inside some very popular systems for a long time has been this type of processing. What Google really pioneered was exposing that to the end users, well, not the end users, but the programmers. Okay, so the kind of systems I worked on, you typed a statement, and this stuff got compiled into something that looked like a MapReduce program. The big breakthrough here was to say, you know what? The languages you can do that for are too limited. Let's open it up to programmers and let programmers see a little bit of the mapping and the reducing, and then that'll let them solve even more problems. And that really is what Google pioneered, and it was a big deal. That's why it's gotten so popular. The Google implementation of MapReduce is proprietary. You can't get to it unless you work there. But a bunch of people started an open source project called Hadoop. I don't have clickers ready here, but well, you guys have all heard about Hadoop because you played with it already. I should have asked last time. But Hadoop is it's a big deal in industry right now. A lot of people are excited about it. It started at Yahoo, I believe, or at least very early. Yahoo brought it in-house and was sort of the main place where the work was being done. But it's used really all over the place. This slide was a couple of years old. You wouldn't list the places where Hadoop's used now because it's used all over the place. All right? So Hadoop is an implementation of MapReduce. MapReduce is a programming model. Hadoop is an implementation of that programming model. Okay, and what's it used for? All sorts of stuff. Google talks about how they use it to crawl the web and to build that index of 1 trillion pages. How to do things like Google News, where you cluster articles based on their content. Machine translation, if you've ever used the translate function, it works incredibly well. It does that by looking at lots and lots of examples. It's all statistical. It actually doesn't really understand your language. And maps, things like street maps and putting different layers of content on maps and rendering those, also done with MapReduce. All places are using it for spam detection, for ad optimization, for anything that sort of breaks into this nice data parallel model where you've got a lot of information that you have to churn through, and you want to look through it not one by one, but you want to look through big chunks of it all at the same time. All right? So it's used for a lot of things. Okay, I don't know if you can see this one. This is really just a wonderful example. So there's a lot of buzz right now about what people are calling big data or big data analytics. And the idea in a nutshell is, organizations are collecting all sorts of information. There's hidden, insight and value in there. And if we could only figure out the right algorithms and be able to churn through it fast enough, we'd be able to find out important facts about the world and humanity. And so this is an example of that. This is something that Facebook used to have up, and they took it down about 2 years ago. Facebook Lexicon. It was really a lot of fun. And you could type in terms, and then it would graph for you over time how often those terms showed up in people's status updates. Okay? So what could we learn about the world here? All right. So the blue is party tonight. So that's the number of times, and it's all relative, but that's the number of times that the term party tonight shows up in my status update. And the yellow is hangover. How many times does the word hangover show up in my status update? So what can we learn about the world? Oh, it's fascinating. Well, you see this first cycle, okay? That's the weekly cycle. People tend to party more on the weekends. Not everybody's in college. So most people have to do their partying on the weekends. And that's what that spike is. So you see that. Not surprisingly, you'll notice there's about a 1-day lag between the peak of party tonight and the peak of hangover. That's expected, so that's probably not that interesting. And then, I don't know if you can read it. This is January 1st, so everyone knows what that spike is. That's New Year's. This is interesting. Here's October 31st. Halloween. It's Halloween, but this is October 31st here. This is a couple days before. So what do? So now you got to put on your data analytics hat. So I went back, I did some research, I brought up the calendar from 2007, and sure enough, Halloween showed up on a Wednesday night that year, and so that was the Saturday night before Halloween. So, this is what it's all about, is understanding things like this. Like you didn't know before that hangovers happen after the party, but now you have scientific proof. Okay, but in order to do that, think about what they're doing. They're churning through all the status updates of at that time, 250 million people, now 600 or 700 million people that are on Facebook. That's a lot of data to go through, and if you want to give a quick answer to that, you need a way of looking at a bunch of data all at the same time. So that's what this is all about. So, what's MapReduce for? As we said, scalability. You want to go up to thousands of machines, tens of thousands of disks, and you want to be able to do it cheaply, or as cheap as possible, so you want to be able to use commodity servers. You don't want to have to build these gold-plated servers. You want to build the ones like we looked at last time that have a little battery kind of velcroed in and things like that, because those are going to be cheaper. So the problem is they fail more often. That's why you need fault tolerance even more. Okay? This is the famous paper that described MapReduce. If you haven't seen it, you might want to take a look at it. So what is MapReduce? Well, you guys actually already know this, so I'll go quick. But basically, there's a map function which applies to individual records, okay, and generates an intermediate set of pairs of a key, which is a unique identifier and some value, okay, which is usually a number. It doesn't have to be. And then once you have a bunch of those things, what you want to do is what's called a reduction, where you take all the items that have the same key and you combine them in some way, you aggregate them in some way, and typically you add them up is the most typical. That's how you'd get that graph we just looked at. you would look over all your servers for all the instances of party tonight, and all those servers would report that back, and then you'd add up all those counts, right? So each server would tell you how many times they had party tonight every day, and then the reducer would take those and add them all up and give you a final answer. Okay? All right, so where do the map and reduce operations come from? Well, you write them in your favorite programming language, as long as it's Java or Python. It's split in such a way that then, given that, the system can parallelize it, and it can also, fix up problems. If a particular mapper or a particular reducer dies, it can get started up somewhere else, and the system handles all that. Hadoop or MapReduce is going to handle that for you. Okay, that's the fault tolerance part. Okay, so kind of already said this. It's based on splitting the data into pieces, or what's sometimes called shards. And then, maps are applied on each of those shards. And then each of the shards reports back, and those are all combined in the reducer. Okay? And fun to use. I guess I'll let you guys judge that when you see Project 2. But the idea is, you get to focus on your problem. You don't have to worry about the fact that we're going to be running on EC2, and maybe it's happening on EC2's cluster up in Seattle. Maybe it's actually running on EC2's cluster in Virginia, or maybe it's running somewhere else. You don't have to worry about which machines it's on or it's failing or whatever. The system's going to handle that for you. That's abstraction. Thank you. So, what does this look like? You shouldn't be surprised at what this looks like in terms of hardware, right? This is a different version of what we saw before. You have a rack of servers. Each server has its processor and its local disk. There's a switch that lets servers on the same rack talk to each other. And then there's a bigger switch that's used for the whole array that lets communication happen from this rack to this rack. Okay? And then I'm not going to go through these, but these are just some numbers from a Yahoo Hadoop cluster from a couple of years ago. So you can look at those just for scale. This is one picture of how it's going to work. The data is split into little pieces here. Those are mapped. Intermediate results come out. Those get grouped by the key. Okay, so here's key 1, key 1, key 2, key 1, key 3, key 4. Those get grouped. All the key 1s get put here. Then you've got all the... Ooh, I might have just ran out your battery here. You've got all the values for key 1, all the values for key 2, all the values for key 3. You then reduce those into hopefully a single value, and then you're done. Well, no, you're not quite done. Then you have individual values. Then you got to kind of put those together to get the final answer. Although Hadoop doesn't do that for you. You got to do it yourself. Okay. So this is pseudocode that's a little weird because it makes this kind of silly assumption. But just so you can see it, and I've got another version of it after this. But this is the mapper, and it basically says for each word W in this input value. So I'm looking at some sort of input string. It's got a bunch of words in it. For each one, I'm gonna emit that word and the number 1. Okay? So if I wanted to count all the words, what I do is I put out a bunch of key values, key value pairs. Key is the word, and the value is a 1. So if I want to find out how many times a particular word shows up, I just take all the keys, all the pairs where that word is the key, and I just sum up all their values, all the 1s, and that gives me the answer. Okay, so map is producing that list of intermediate results, which is a word and a 1, and then those get sent to the reducers, where the reduce basically says, hey, for each thing that has that word, increment the result, and then once I've seen them all, I'll spit out the result. Okay, that was in some weird pseudocode. This is what it looks like in Python, and it's actually, if you speak Python, which I don't particularly, but it actually makes more sense. So, here for each word in the input line, we're going to output the word in lowercase, right? So that whether I say Dan with a capital D or a lower d, it'll still show up as Dan. And then I add, with a 1. So that's what we were doing in the mapper before. And then here's my reducer. I have to take the input line. The first thing is the word. The second thing is the count. And then basically I just take my current total for that word and I increment it by the count. Okay? And then once I'm done, once I've gone through all my lines, then I spit out for each word the count. Okay? So, okay, so what does that look like? That was in Python. What's it look like in PowerPoint? I'm sure you were wondering that. So here's what it looks like in PowerPoint, which is really the language I'm best at these days, unfortunately. So, we're going to count words, right? So how many times do words appear? So we can split this thing up. It's so big, we're going to split it across 4 machines, right? So there are 4 mappers, okay? And each mapper basically looks at what it's got. And you can see that map 1 has the word is once and the word that twice. And this one has is once and that twice, and this has is twice and not twice, and so on. Okay? So those are your intermediate results. Then you send those to reducers. And then here's the tricky part. For those of you talking, this is really the tricky part. You have to decide for each key where it's going to go. Okay? Because it doesn't help you in the reduce phase to send some of the is's over here and some of them over here, because then you'll still have to do another reduction. Okay? So if you want to do this kind of in one step, you got to make sure all the is's go to the same place, right? And likewise, all the that's go to the same place. So you use basically some sort of a hash function, right? And you say, you know, is's go there, that's go there. Cool. So let's go. That's what happens to the results from map 1. Here, is's go to reduce 1, that's going to reduce 2, so we're done there. What's going to happen here? Well, the is's from map 3 better go over here. The not, we're not sure where that's going to end up because we don't know the hash function. Oh, that ended up over here. And then is, that, and so on. So you've got now everything partitioned, right? So it's all parallelism by partitioning things. And you don't, if you want to know how many is's, how many times does is show up, if you were Bill Clinton, for example, that joke might be too old for you guys. You know, they're all in reduce 1. You don't have to look at reduce 2. That's kind of the key idea. You got to partition the thing. Okay? Once you got that, so, oh, guess what? So that's how many times each thing shows up. And we were able to do it in parallel. This is where Hadoop kind of leaves you. I've got a bunch of results in reduce 1, results in reduce 2. It's not a big step to kind of pull those together. Okay? And you don't have to, by the way, you're not aggregating, right? The important thing is when you go from all these different maps to reduce, you actually have things with the same key coming in, and you have to somehow sum up or add up or do whatever you're going to do to those counts. Here, in this collection phase, it's a union, right? Because we know that no keys show up in more than one place. So we don't have to worry about aggregating things, we're just unioning them. Yeah? Yeah, I'll show you what that looks like in a second. Yeah, but the question is, you're sending more than data. You must be sending code too. Otherwise, how does the machine know what to run? And you're exactly right. Yeah, that's what Hadoop does for you. Yeah.
So during the shuffle, do they try and split up the keys so that each reduce like machine?
Yeah. So the question is, for the shuffle, do they try to split the work fairly across the different reducers? And the answer is The answer is yes, they try. And some of the challenge in building a system like Hadoop is to be smart. You know, there's some obvious things. This idea of just, you know, the idea of just using a simple hash function may or may not work depending on the problem you're trying to solve. No, it does. See, it doesn't matter how many is's there are so much, right? It matters how many different words would hash to that reduce. Right. But yeah, you can. So Hadoop, no. Hadoop does things very simply and basic. It just does a hash. But there are research systems that try to do smart. They do sampling of the data. They try to do something adaptive that changes over time. All that stuff. That's what, you know, a lot of people trying to get their PhDs now are working on stuff like that. Yeah. Yeah, it would. So good question. So would it help to have another layer of reduce function? And the answer is yes, although typically you sort of take the results of the reduce and go through a whole map. You map those and then reduce. So you typically do iterations of maps and reduces. So map, reduce, and keep going. Okay? All right. So, okay, so to answer the earlier question on answer the code, so what happens is you have all these different machines, and Hadoop has to sort of decide, well, you have to tell Hadoop what machines it gets to use. Okay, and those might be physical machines. More likely, they're going to be virtual machines, which adds another level of complexity. Okay, to making this work well. But there's some number of machines that you give Hadoop, and you can give Hadoop some hints about sort of the minimum number of maps you should have, the minimum number of reducers you should have. And then Hadoop is going to be very kind of promiscuous, I guess is the word, in terms of using extra resources if it can find it. Okay, so there's a whole bunch of knobs you get to turn about sort of how the work gets spread out. But at the end of the day, Hadoop is also going to do its own optimizations to try to take advantage of extra hardware, mostly. So, so you're at the top here. You submit your program. That gets sent to the master. All right. So the input has to get split into multiple files, right? So because each worker is going to read one or more files. And there's actually, it's not on this slide, but the way you do this, and the way I think you guys can do it in the project, is there's a file system called HDFS, the Hadoop Distributed File System, and that takes care of the splitting for you. Okay, so you think you have a single file. HDFS is actually splitting it across multiple machines, and then it's actually replicating it 3 times. But you don't see any of that. Okay? But so the data gets split, put into files. Okay? Then there's a special worker called or a special node called the master, and the master looks for places where it looks for machines where it can that aren't fully occupied. So a machine has a certain number of worker threads it's allowed to run. The master finds machines that are available, and then it starts sending them. It assigns map jobs and reduce jobs to those available machines. Okay, that's the next step. A worker then, reads its part of the data, okay, and basically applies the maps to it. Okay, so each worker is looking at a different part of the data set. So here, this worker is looking at parts 0 and 1. This one's looking at part 2. This one's looking at part 3. This one's also looking at part 4. And basically it reads one, processes it. If it still has availability, it reads the next one, and so on. Okay, so that's where maps happen. And maps then generate these intermediate results. These results, interestingly, get written to disk. Okay, why do they get written to disk? Fault tolerance. Okay, if a machine dies, it'd be nice if you didn't lose the intermediate results. So periodically, stuff gets written to the disk. Once the maps are done, you can then start the shuffle phase. Okay, so the data, the intermediate results get sent to this other set of workers using that shuffle step that we just showed you based on hashing or something else. Okay? The workers run, the reducers run the reduce task. Okay, and when they're done, they write an output file. And like I said, that's kind of where Hadoop leaves you. You end up with a distributed result that you then, in your own collection phase, need to pull together. So let's see. I think there's a question back there first. Yep. So how big effect does writing the data to disk have? Yeah. So great question. So the question was, boy, that seems really expensive to have to write that data to disk all the time. And it absolutely is. And we actually have a project here in our group, in the lab, the AMP lab, called Spark, where one of the things Spark does is it gives you fault tolerance without having to write stuff to disk. And it does it by cleverly replicating things. So that's one of the, so you've identified one of the big performance problems with Hadoop. So, but if you use vanilla Hadoop, that's what you get. It's pretty surprising that it works at all. Yeah. Uh-huh. Oh. Okay, great question. So every time somebody does a search, is something like this happening? Or is this only for larger tasks? It's a great question. I'm not sure I know the answer exactly. But this is definitely what you do for larger tasks. For requests, for a search, you're going to try to do some sort of parallelism, but you wouldn't use MapReduce. You would have some other way of splitting the work across multiple servers. So you still want, I talked about web search as if it was only request parallelism, that your request runs in parallel with mine. But each request is done in parallel because remember that index is really big. Okay, but you don't want to use MapReduce for that because MapReduce is what's called a batch process. You load a file, You process it for a long time, spit out the answer. And you don't have time to do that in an interactive situation like a web search. So they have other mechanisms for doing that. Yeah, one more question, yeah. Oh, two more. What's that? Okay, why do you have to make copies? So why do you have to make copies in the initial storage? The reason you make copies in the initial storage is oftentimes the file is already there, right? Because let's say you're collecting, log records from, let's say you're running a web server and that thing's spitting out log records. Typically, you write those to a file. At some point later, somebody starts MapReduce in order to do some analysis to find out if hangovers follow parties, and you don't know. You don't know at the time somebody runs that MapReduce which servers are going to have extra capacity, right? So having 3 copies gives you 3 chances to find a server that has capacity. And furthermore, one of those might be down. So that gives you chance for 2 others to work. Yeah, one more, and then I want to give Dan a little time. Yeah?
Yeah, so my question is that, you know how one split goes to one worker? Would it make more sense to send that same split to multiple workers? Because if one of the workers was like a bad computer that just added wrong or something,
yeah.
kind of conflict resolution.
Okay. Okay, great question. Wow. Okay, so, if you're following this discussion and you're interested in this discussion, I want to talk to you about grad school because this is exactly, given a fairly complex system like this that has some obvious things that it's doing that you could think you could do better, what are those? And that's how we spend most of our time when we're not making exams and grading them. That's what we think about this kind of stuff. So, come talk to me. So the question is, why don't I send that to multiple places? And the reason you gave was in case one of the workers is faulty. Okay, then maybe you could have a vote, and whoever has the right answer wins. In general, for these types of things, the processing's deterministic, so that never happens. But there are definitely things like machine learning algorithms, sampling, fancy things you do where you can easily get a wrong answer. And in that case, you might want to do that, and Hadoop doesn't do that for you. You'd need another system. But the other reason that you might send it to multiple places is I think what's next. This is just the timeline of things that happen looking a different way. This is why you might send it to multiple places. Because every once in a while, a system gets slow. Okay? So here, if a worker fails, you say, hey, this worker failed, right? You try to talk to it. A heartbeat is you say, hey, are you there? And it comes back and says, yeah, I'm still there. Okay? If you say, hey, are you there? And you wait for a while and you don't get an answer, then you assume that system's down. So what you do is you start the job up somewhere else. That's one of the reasons why you have 3 copies. Okay? All right. But so that's if a worker fails. If a master fails, that's a whole nother research topic. But there are systems. There's a system, an open source system called Zookeeper that basically does a new election for a new master. We're not going to go into that. That's the operating systems class. You talk about it there. This is, I think, a story from Google, which is, some story about them losing, 80% of the machines and it's still working. Okay, whatever. But the other thing to answer your question is that even if there's not a failure, sometimes workers get slowed down because they've got, because that hashing didn't give you a nice even distribution. Okay. Or maybe there's some problem. Maybe some of your machines are slower than others. Okay, or maybe somebody misconfigured, right? Maybe they didn't come to the earlier lectures on caching, and when they set up the machine, they disabled the processor cache. There's a bunch of reasons why systems might be slow. So what happens is if you're waiting for a while and you're not getting an answer, so you're almost done with that map phase, and there's a few places you haven't heard from, what Hadoop does is it starts up other copies, and then whichever one finishes first, you take that, because again, things are deterministic. You're going to get the same answer. Okay, so whoever finishes first wins. All right, so with that, I wanted to just summarize. We've got a couple minutes for a quick clicker question. But basically, to summarize, talked about 2 types. Don't go on us, because we have a clicker question. Okay, you're getting out your clickers. Good. Okay, request level parallelism. I ask a question, you ask a different question. We get to run those at the same time. Data level parallelism, it's one big question, but we're applying it to lots of data. So why don't we take the application to each piece of data and try to do that at the same time. And we talked about one particular way of doing data parallelism across multiple servers called MapReduce. On Monday, we'll talk about another way of doing data parallelism in memory with special instructions. And with that, I would like to turn over to Dan. Yeah, you want the, I'll give you this. All right, so this is either a test of our exam or a test of your opinion of your own knowledge of the class. So question number 1 is, how did you do on the exam? Do we have to wait till you have it up and running? Okay, so how did you do on the exam? If you thought you did right at the mean, C, then a little less B, a lot less A, a little more D, and if you're really, really confident, E. Oh, look at that. Okay. You want to do the other one?
Yeah. And don't change it, right? Be honest. By the way, this is a very, I don't know if this is we have more seats that are open now post midterm than I was hoping. So come back, people who are not in the class. So don't come on. So that's that one. So let me freeze that one. And then, okay, that's probably expected. And now we're going to do the second question, which is over here. And then I'll get a chance to answer the question that was asked of me last Friday, I think. Okay, and now go. Compared to what you expected. So how is this compared to what you expected? Hopefully not too different in terms of HKN giving you a real expectations, the kind of quick quizzes we ask in 61C. Okay. So some folks thought it was a little bit harder, so I was hoping for more C's, D's, and E's. Okay. So there's that one, and you can keep voting. And then the last wing is that there was a pending question on how is it possible that multiple compilers can compile, that Rohan has helped me with the answer with that one. That was actually in the book. It's Appendix B, we understand. So it turns out that how can it is possible that independent compilers on independent, like foo.c's, all name the same thing, can create their own labels, because you have to make labels when you do these branches, so that you need to have these artificial labels. But then how are those branches not somehow colliding in the same namespace? And the secret is, in the header file, when you're making the assembler, you can say, see that label right there? Don't add that to the symbol table at the next level. Right? Because the next level down, it's compiling assembler linker loader. The assembler's job is to build the symbol table, to build the relocation table, to the linker does the right job. So you can pass on metadata to say these tags, ignore those, the user didn't give those to use, those are the ones that I created myself, those are not to be shared. So only things like a function call, obviously that might be shared, but an internal label for a loop wouldn't be shared at the next level of the assembler. And that's how we don't have this name collision. Okay? Good. All right, so the summary on the exam is we're going to try to get this graded. The TA is going to work really hard this weekend to give it to you. You saw the answers. We already have the rubrics all ready to go. We're going to go for partial credit like crazy. So that's every TA was told, go for partial credit on every single question. Very few are going to be right or wrong, but maybe a couple of them. We'll try to get the back end discussion next week. So we'll talk about the exam next week. Okay, thanks.